Hello, class. All right. This is Math 1430. I'm Dave, and as you can see, we're doing 14. We're Math 1430, Section 4.2, Applications of the Second Derivative. Let f of x equal x cubed minus 3x squared plus x minus 2. Determine the intervals on which the graph is concave up, concave down, and we also want to find inflection points. So concavity is always an f double prime problem. So whenever you're asked on what intervals are we concave up, concave down, that's an f double prime problem. Likewise with inflection points, that's an f double prime problem. So for a solution, this is a second derivative problem. So let's find f double prime of x. And then we can get what's called possible points of inflection. And how do we get those possible points of inflection? By setting f double prime of x equal to 0, or where is it undefined? Those are the two ways. So when is it equal to 0? Or that says or where is f double prime of x undefined? At what x values? And these two together will give you possible points of inflection. And then what you want to do is plot them on the f double prime sign chart, and that will form intervals. So let's get to work. Let's find f double prime. Here's our f of x. So the first step for our solution is to find the first derivative, because in order to get the second derivative, you have to run through the first derivative. So the f prime of x, as you know, 3x squared minus 6x plus 1. Remember, derivative of a constant is 0, so you don't have to write plus 0. That doesn't change anything. Now that I got my first derivative, the second derivative is the derivative of this first derivative. So the second derivative, which is what I'm really interested in this problem, again, to do the power rule, 2 times 3 is 6x to the first, which you don't have to write. So 6x minus 6. So this is my second derivative. Is this ever undefined? Is there an x value that makes this undefined for a possible point of inflection? And the answer is no. This function is never undefined. So we are not going to get possible points of inflection that way. So the
It's a
other way,
polynomial function, and the domain of all polynomial functions is all real numbers.
never undefined. So that was my twin brother chiming in. Okay, so the other way to get possible points of inflection is to set that second derivative equal to 0. So let's solve this equation. I'm going to get the x term by itself by adding 6. So 6 is equal to 6x. I'll write it like this. 6x equals 6. Same thing. Dividing by 6, we get x equals 1. So this is our only possible point of inflection, PPI, possible point of inflection. So since we only have one possible point of inflection, we're just going to plot that one point on the f prime sign chart, as I like to call it. And then somewhere, just plot 1. So this is the f double prime sign chart. It's nice to label what you're doing. And now we get two intervals. If you only have one plotted point, you get two intervals. So let me write them down. Our intervals go from negative infinity to 1, right? To the left of 1 goes to negative infinity. And then our next interval is 1 to infinity. Once you get your intervals, you want to choose test points. So what's a good number from negative infinity to 1? You never choose the endpoints because these are open parentheses. How about 0? Isn't 0 inside that interval? I could have chosen negative 1. It doesn't matter. Any test point. I don't need parentheses here. So I'm going to choose the test point 0 for that interval. I'll write x equals 0. Let x equal 0. And then what is the easiest number to choose in this interval?
2
Yeah, how about 2? You could have chosen 3. It doesn't matter.
or 4.
Okay, so now that I got my test points, here's what we're going to do next. You want to plug them in to f double prime. This is called the f double prime sign chart. So plug your test numbers into f double prime. So first I'll plug in x equals 0 in this second derivative. So make sure you go to the correct place. You want to go to the second derivative because this is the f double prime sign chart. So when I input 0 for x, I'm going to get 6 times 0. minus 6. 6 times 0 is just 0. 0 minus 6 is a negative 6. What I'm interested in is the sign. So when I input 0 into my second derivative, I get a negative result. So here's what I like to do. Put negative signs in this interval that includes 0. And whenever your second derivative is negative, that always means concave down. So I'm going to draw a concave down shape. Okay, now let's input f double prime of 2. Let's do this in our heads. When I plug in 2 for x, I'm going to get 6 times 2 is 12. 12 minus 6 is 6, which is positive. Positive. So, for this interval from 1 to infinity, which includes that test number 2, we are positive, which means concave up. Concave up. So this gives us a wealth of information, this f double prime sign chart. So I know from negative infinity to 1, we're concave down. So I'm going to write this down right over here. Here comes my answer, nice and clear. We are concave down on the interval negative infinity to 1. We are concave up. You want to make sure you answer the question clearly. It says, where are we concave up and concave down? So you want to write it clearly. Don't stop here. You want to write your answer clearly. So clearly we are concave up from 1 to infinity. Use parentheses. And whenever you have a change of concavity about a possible point of inflection, that means this possible point actually is a point of inflection, because inflection points are where the concavity changes, either from down to up or up to down. So if you have a change of concavity about a possible point of inflection, that is an inflection point. If you do not have a change, like if this were concave down and this is concave down, then this would not be a point of inflection. So I'm going to write point of inflection, POI, is going to be the x value is 1, but because they ask us to find any inflection points are always x comma y, we know x is 1. So to figure out the y on the graph, make sure you go to your original function, input 1, to get the point on this graph. So when x is 1, 1 cubed is 1, I'm going to get 1 minus 3 is a negative 2, plus 1 is a negative 1, minus 2 is a negative 3. So that is our possible point of inflection. My brother will go back so you can see this whole thing now.
So that is the point of inflection.
Yes, it is a point of inflection. We have one negative 3. And then I'm going to make one more point. Once you see all of this, you can hit pause on your video and then take notes on anything you might want to take notes on. Okay, so let me say one final thing. In the previous section, we talked about where do we have f increasing and decreasing? On what intervals is f increasing and decreasing? Increasing, decreasing questions are first derivative problems. And it's very similar to what I did here. The only difference is if you want to find on what intervals is this graph increasing or decreasing, you would say this is a first derivative problem. So you would find f prime of x to get critical numbers. Instead of possible points of inflection, they're called critical numbers for the first derivative. And remember, your critical numbers and also your possible points of inflection, make sure they're in the domain of the original function. If they're not in the domain, then you must strike them out. They're not going to be your critical points or possible points of inflection. Okay, so once you get your critical numbers by setting the first derivative equal to 0 for intervals of increase, decrease, then you would plot them on the f prime sign chart to form intervals. And then once you get your intervals, you would find test points for each interval, but then you would find f prime of those test points. And then if f prime is positive, that means the graph of f is increasing, and if f prime is negative, that means the graph is decreasing.
Or going downhill for decreasing, a graph is going uphill when it's increasing the slope.
Okay, so that is all. Good night, everyone.